Welcome to Module 6 of our Calculus Exploration. In this module, we'll delve into differentiation rules, which are powerful tools for finding derivatives of functions more efficiently. This section introduces several rules that allow us to differentiate constant functions, power functions, polynomials, exponential functions, rational functions, and certain combinations of them, simply and directly, without having to take limits each time. Differentiation rules provide us with shortcuts for finding derivatives of various functions. We have rules for powers, multiples, sums, and differences of functions, each serving to simplify the differentiation process. Powers, multiples, sums, and differences. A simple rule of differentiation is that the derivative of every constant function is 0. Derivative of a constant function. If f has the constant value f of x equals c, then the derivative of f with respect to x is the derivative with respect to x of c, which equals 0. When we have a function f(x) that is a constant function, it means that for every input x, the output is the constant value c. This function is graphically represented as a horizontal line on the Cartesian plane. The derivative of a function at any point measures the rate at which the function's value is changing at that point. For a constant function, the output value does not change no matter what x is. Hence, the rate of change is 0. Mathematically, the derivative diff over dex is the limit of the difference quotient as h approaches 0, which would normally be the limit as h approaches 0 of f of x plus h minus f of x all divided by h. However, since f of x equals c and f of x plus h equals c for all x and h, the difference f of x plus h minus f of x is always 0. Therefore, when you divide 0 by h and then take the limit as h approaches 0, you still get 0. This gives us the derivative of a constant function, which is 0. The notation d over dex of c means the derivative of the constant with respect to x, which is always 0 because a constant does not vary with x. In essence, the derivative of a constant function is 0 because the function as output does not change as x changes, indicating that the function has a constant rate of change, or rate of 0. The proof is demonstrating how to apply the definition of the derivative to find the derivative of a constant function and establishing a general rule for differentiating powers of x. The first, derivative of a constant function. For a constant function f of x equals c, where c is a constant, the derivative f prime of x is found by taking the limit as h approaches 0 of the difference quotient f of x plus h minus f of x over h. Since f of x is constant, f of x plus h and f of x are both equal to c, and their difference is 0. Thus, the quotient is 0 over h, which is 0 for all h not equal to 0. The limit of this expression as h approaches 0 is also 0. Therefore, prime of x equals 0. The second, derivative of 1 over x. The proof recalls from section 3.1 that the derivative of 1 over x with respect to x is negative 1 over x squared. This is also expressed using the power of x as the derivative with respect to x of 1 over x is the derivative with respect to x of x to the power of negative 1, which is negative x to the power of negative 2. The third part, derivative of the square root of x. The proof also reminds us from an earlier example that the derivative of the square root of x with respect to x is 1 over 2 times the square root of x, which can be written using the power of x as the derivative with respect to x of the square root of x is the derivative with respect to x of x to the power of 1/2, which is 1/2 times x to the power of negative 1/2. Let us continue with the power rule, which tells us how to find the derivative of a function raised to a constant power. The rule states that we bring down the exponent and multiply it by the coefficient, then decrease the exponent by 1. Further in this article, we will explore the concept of power rule derivatives and its formula. We will also prove the general formula of the power rule and understand its application with the help of various solved examples for a better understanding. Power rule. The power rule for differentiation is used to differentiate algebraic expressions with power. That is, if the algebraic expression is of form x to the power of n, where n is a real number. Then we use the power rule to differentiate it. Using this rule, the derivative of x to the n is written as the power multiplied by the expression, and we reduce the power by 1. So the derivative of x to the n is written as n times x to the power of n minus 1. This implies the power rule derivative is also used for fractional powers and negative powers along with positive powers. The power rule can be used to differentiate polynomials. Power rule in calculus is used for various types of functions and for different purposes, which we will discuss later in this article. The next rule says that when a differentiable function is multiplied by a constant, its derivative is multiplied by the same constant. Derivative constant multiple rule. If u is a differentiable function of x and c is a constant, then the derivative of c times u with respect to x equals c times the derivative of u with respect to x. In particular, if n is any real number, then the derivative of c times x to the n with respect to x equals c times n times x to the n minus 1. Certainly, let us consider the function f of x equals 5 times x cubed. Using the constant multiple rule, we can find the derivative of f with respect to x as follows. The derivative of 5 times x cubed with respect to x is equal to 5 times the derivative of x cubed with respect to x. Now we apply the power rule to x cubed. The derivative of x cubed is 3 times x squared. So the derivative of 5 times x cubed is 5 times 3 times x squared, which simplifies to 15 times x squared. Therefore, the derivative of f of x equals 5 times x cubed with respect to x is 15 times x squared. Next, we have the sum and difference rules, which tell us how to find the derivative of a sum or difference of functions. The rules state that we can differentiate each function separately and then add or subtract the derivatives. The next rule says that the derivative of the sum of two differentiable functions is the sum of their derivatives. Derivative sum rule. If u and v are differentiable functions of x, then their sum u plus v is differentiable at every point where u and v are both differentiable. At such points, the derivative of u plus v with respect to x equals the derivative of u with respect to x plus the derivative of v with respect to. Proof. We apply the definition of the derivative to f of x equals u of x plus v of x. The derivative of u of x plus v of x with respect to x equals the limit as h approaches 0 of u of x plus h plus v of x plus h minus u of x plus v of x all over h. This equals the limit as h approaches 0 of u of x plus h minus u of x over h plus v of x plus h minus v of x over h, which simplifies to the limit as h approaches 0 of u of x plus h minus u of x over h, plus the limit as h approaches 0 of v of x plus h minus v of x over h. This is equal to the derivative of u with respect to x plus the derivative of v with respect to x. Combining the sum rule with the constant multiple rule gives the difference rule, which says that the derivative of a difference of differentiable functions is the difference of their derivatives. The derivative with respect to x of u minus v equals the derivative with respect to x of u plus negative 1 times v. This equals the derivative of u with respect to x plus negative 1 times the derivative of v with respect to x. Simplifying this, we get the derivative of u with respect to x minus the derivative of v with respect to x. These rules make it easy to find derivatives of more complex functions by breaking them down into simpler components and applying the rules accordingly. Narrator. By understanding and applying these differentiation rules, we can tackle a wide range of problems in calculus and solve them with ease. To sum up in this module, we explored differentiation rules, including the power, sum difference, and multiple rules. We learned how these rules provide shortcuts for finding derivatives of various functions more efficiently. Thank you for joining us in Module 6. In our next module, we'll delve into the derivatives of exponential functions and explore their significance in calculus. See you there.